I will show you how to use the software. Then, where was it? Here we go. In this class, we would like to use the software to achieve this. Okay, this is a video I downloaded from YouTube and slow motion of the soccer player kicking the ball. Okay. And here, on your computer, you can see I track this part, and ball, right? Okay. And I use digital image correlation to track it. So this is what we are going to achieve. Good. Okay, that's the end goal. Are we okay? Good. This is we would like to think about this as a cooking show, お料理クラス. Okay. This is we are going to cook. Got it? Okay. All right. All right. Then and the homework. Homework is something like this. Okay. Homework is here you go. This is a video of my finger. Okay. Captured it. All right. Then you will track the finger segment. Where's my here you go. Yeah, as you can see, it's tracking, right? Good. Then using that software, the displacement or position of all the in that video I tracked 1, 2, 3, 4 points. Okay. Then eventually it will spit out this Excel. Okay. The first page is the position. Okay. I tracked 4 points, so I have blue points, red points. You can see X, Y, X, Y, X, Y, X, Y, 4 points. Okay. And between 4 points, we can define 3 lines, right? Or 3 vectors. Then vector information is here. Then you can see here is the length of the first vector, angle of the first vector, so on and so forth. Good. All right. So this is the homework you should try to execute. Are we okay? Good. All right. Then before that, I would like to go through the short explanation of the lecture. All right. So motion tracking. Okay. All right. So motion tracking, right? Okay. Good. First of all, digital image, right? Digital image, and you can track the color image. Color image consists 3 layers, right? Green, blue, red. Okay, but most people usually convert the color image into grayscale. Grayscale has only 1 number, so this is what we're going to handle. Even we may start from the color image, but we will convert it into a black and white, then track it. Okay. So this is the grayscale digital image of my dog, Inu. I named him Inu. Yeah. He's 100 pounds. 50 kilo. Great, yeah. And every morning, 4 a.m., he will lick my face. Yeah. Anyway, so this is the digital image, right? And the black and white space, the black part is 0 magnitude. The highest number is the white, that is 255. The total is 256 level, right? Okay, that is the basic structure of the black and white image. So since each pixel is numbered, so if you want to present this as heat map, makes sense, right? You can do so, right? Right? White is very high, that means very hot, right? Black part is very low, that means very cold, right? Okay, you can present that way, or if you want to present as 3D plot, like mountain geography, you can do so. Right? This part is obviously very high. This part is the pixel intensity. Good? Are we okay? Okay. So this is the basic structure of the black and white or grayscale digital image. Good? All right. Then now I would like to talk about why tracking is important. And this example is not so peaceful. Here I track the I think a cargo airplane. I download it's doing the rolling. Okay, then you can see
It's tracking. Good? Okay. And why we need to track it? It's a very not so peaceful example. But let's say we work for Mitsubishi Radar Company or making missiles. Good? Right? Okay? And let's say you want to shoot down enemy airplane. Good? The enemy airplane is rolling right now. Are you with me? Good? Enemy airplane is here right now. My airplane is pointing that way. Missile is pointing that way. If I shoot, what will happen? If I shoot the missile, this is the current position of the enemy airplane. If I shoot my missile now, what will happen? It will miss, right? Right? Of course, today's missile has a tracking algorithm and radar, so it will not miss. But let's say we're using very old-fashioned missile, it will go straight and miss it, correct? Right? Then that means we need to predict this motion, right? From this known position to calculate the measure. From here you can predict the future angle. Then you should shoot for target that future position, right? Then you can shoot it down, right? Okay, so that's the one of the justification. Again, it's not a peaceful example. That's why we need to measure. We can measure position of the object visually using the computer vision. Okay, and from here to here, using my software, what you can do is first video frame. Okay, then you select the obvious location. Okay. This propeller here is blurred, not clear. Usually that kind of image is hard to track. So you have to pick a very crispy corner. That kind of pattern is much easier to track. Okay, so that's the first thing we have to know. When you use a tracking algorithm, you have to pick a very sharp corners. Okay, all right. Then once that's done, tracking algorithm will track everything, right? Then each time position is tracked, right? Then 2 points tracked, then you can define the vector, right? You can define the vector, it's a vector calculus, right? Then that's the frame 1. Then frame 2, okay? Then this position moved to here, this position moved to here. Then vector change the angle to here, right? Then to find out the angle between these two vectors, what do we use? Do you remember? What kind of mathematical tool we can use to calculate the angle between two vectors? Nicety. Inner product, right? Then you can use the inner product to find out the theta, right? Okay, then computer can do it really quickly. So by doing so, you can find out airplane from here, this is angle, change. This is measured from that video, jumping around, but you can still see there's a clear pattern, right? Trend line. Okay, then you can quickly calculate the function as angle as a function of time. Then after that, it can predict using the extrapolation technique. You can predict the future angle of the airplane will be here. Then missile and target capture. Good. Okay. All right. So that's the justification. All right. Okay. And motion tracking algorithm can be used to track the video frame that is recorded along time axis, right? Video image, each image is a 2D X and Y, but all of them are recorded as a time functions, frame 1, frame 2, frame 3, along the time axis, right? Of course, that's the way we do motion tracking. But just like any engineering problem, if you know how to do this, actually we can use this to create the 3D reconstruction, right? MRI image will can scan your body 1, 2, 3, 4, 5 in Z direction, right? Good. Then if you want to, each image is 2D, but eventually you can stack it up, right? Then we have a Z direction equivalent to T direction. Then you stack up everything, then you track this point to this point, this point to this point, okay? Then connect all of them, then you can do the 3D reconstruction. Good? Right? That's why I think the engineering is fun. You learn one thing, and highly possible you can apply to other cool things. Yeah. All right. Okay, then I'm going to talk about. Oh, here is the video of the tracking of the supraspinatus shoulder tendon. This is the cross section of the shoulder tendon, and what I did was using ultrasound to slide gradually to track this shape, okay? In a very crude manner. Yeah, you can do it. So, right? So that means as long as if I would like to, I can reconstruct the entire 3D shape of the supraspinatus. Okay. All right. Good. Okay, so today I'm going to talk about 3 kinds of image tracking algorithm. Okay. The first one is called optical flow. Optical flow, basic idea is try to track the pixel. Okay, that's the idea, right? Okay. We don't need to go through this. We talked about yesterday already, so I will skip this. Okay. All right. All right. Optical flow. It's a pixel-based tracking. Good. All right. And we talked about it, right? This is the sort of the 3D image of the pixel intensity in one frame, right? Okay. Then in video, we can capture the pixel intensity at time t. Then after that, we have another video frame recorded at delta t, right? Good? Okay. To understand the motion tracking, we just need to understand one tracking of the pixel from one frame to next frame. If you can do so, execution from after that is consecutive, very simple. Okay? So the big assumption here is the pixel of one point in one frame is exactly same as the pixel intensity, brightness is exactly same as the pixel intensity in next frame. Okay? But that same pixel may move to dx and dy. Right? Is it true? Not quite true, but usually when we do the motion tracking, we will use high-speed frame rate camera. So the motion can be assumed to be very small. So this is pretty much an acceptable fact. Good? So if you look at one pixel at the time located at xy, that is the intensity. Okay? That same pixel in next kind of frame, dt, move to dx and dy. Right? That's the equation we are going to handle. Okay. Right. Okay, again, I go du. Okay. Right. Let's say we captured him at the frame t, time t, and I'm interested in his nose part. Okay, I draw up. Right, the center point is quite right, right? Okay, right means high value, and I checked it, it was 153. Good. Let's say he moves slightly this way. Okay, right? I'm looking at same box. No, actually, I'm not looking at same box. Slightly off location. Okay. Then in the center, it's darker now. Dark region is coming in. So brightness is 87. Okay. Then this center, let's say, we still do not know, move dx and dy. Good?
Okay, so that's the picture we're looking at. Okay, and later we will use it. The slope of the gradient or slope of the brightness change, delta I over delta T is in this case 87 minus 153, and the dt, delta T in this case, frame rate, from the frame rate I was able to calculate that is 0.02. Good. Okay. Right. So more equations. Right. So this is sort of accepted fact. Okay. If you look at the pixel, one pixel located at the xy time t in next frame at the t plus dt, it moved to dx in dy. But movement is small and frame rate is really high. We assume two brightness or pixel intensity is same. Good. Then every time there is a slight change in position or time, right? Calculus teacher would like us to do the Taylor expansion, right? Get first order, higher order. Okay, always miraculously we say we don't need to worry about the higher order, right? So we can ignore this. Good. All right. So this equation after Taylor expansion near x and y. Okay. This is the first order term and the higher order term again. As a usual practice, we ignore it. Okay. Then we can plug this into this side. Good. Okay. Plug this into this side, but you can see I have an I measured at x, y, t. This is exactly same as this. So this cancels this one. So again, we will only have this term, and that should be equal to 0. That is the equation everybody uses in the world of optical tracking. Good? Okay? Thank you. Okay. So in this equation, delta t is the frame rate, 0.01 or 0.02. This we know. Okay? Delta x, delta y is the movement of the pixel. We don't know. Right? Okay, and what is this? What this I differentiated by x, I differentiated by y, I differentiated by time. What are they? Can we measure? Actually, we can measure. Okay? This is the pixel slope or pixel change in space. Okay? Right. So this, if we digitize it, it will look like it. Okay? Right? So delta I pixel difference between one pixel to next pixel. Dx is the distance we can measure in this map. Same thing. Pixel brightness change in y direction we can measure from one in this same space, in the same frame, and delta x, delta y can be measured. So this can be measured using the current frame. You can use the next frame too, but usually people will use the current frame to calculate this slope. So we can measure it, right? This time, slope, pixel change with respect to time is this one, right? We just talked about it. Okay, this can be calculated by looking at one pixel from one frame to next frame. You can calculate. So now we have these two. And delta t in this case is 0.02, so this is also known. So almost a happy ending, but delta x, delta y, we don't know, right? One equation, two unknowns. Can we solve this? Right? How many equations we need? Two. At least we need two, right? Okay, so right. Oh, actually, I should talk about that. Aperture problem. Okay. Here is the black stripe. Okay. When you see this, how do you feel? This object is moving that way or moving this way? Everybody feels like this object is moving that way, right? Okay. Actually, the creator of this video, he moved this strip in that direction. However, because of this slope, when we see it, looks like this line is moving that way. Okay, that is caused by this problem. One equation with two unknowns. So we will get illusion of moving one direction. That is called aperture problem. And to solve this problem, we need more equations. Okay? All right, and here is the solution. Okay? If we look at one small patch of my Inu, okay, let's say this is the point we will track, but we can assume the point near or around this center point should be moving at about the same velocity, right? Right? We are not talking about big area. So by again introducing this second assumption of small neighborhood will move at the same velocity, Vx, Vy, then suddenly we have, in this image, this is the target pixel, but suddenly we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pixel can be set up using the same equation. Okay. 9 equation can be set up, 9 equation, okay, all the way to 9. Then we can set up this matrix, velocity vector, brightness change in time can be set up. Now we have plenty of information. I just need to find out two unknowns here, right? Then use the least square that we talked about yesterday. Then now we have a square 2 by 2 matrix. This can be inverse. Then solving this, you can find out velocity of this point in x direction and y direction. Okay? Usually optical for researcher, they are more interested in the velocity vector instead of displacement. Okay? But if you can find out this, displacement is easy to find because displacement is simply velocity vector times dt. So and so forth. Good? Alright. Okay. It is a quite powerful tool. Okay. I grabbed this image from the MATLAB. Basically, it will compute two image frame. Each time it will calculate, as you can see, this yellow vector is the velocity vector. Good? All right. It can do a quick, very fast calculation, but one problem is optical flow is not so good at handling the if the image is not crispy, this one is very crispy, white, gray, then it's easier to do. But if you have a grayscale image, it tends to fail. Okay? All right. Then next part is the technique that I used in my research and this software we are going to use. Okay? This is called digital image correlation. Simplified version is called block matching. Good? All right. Okay, here we go. Right? Let's say I use a very crude digital camera. In a frame 1, my dog is here. In frame 2, my dog moves to here, right? Good? Okay. And if I ask you what's the displacement of the Inu, everybody can say, look at here. This is Inu. You memorize it. You come to this frame. No, this is not Inu, this is not, this is not, this is not, this is Inu, right? Then you can say, Inu, you did the pattern recognition and registration, say this Inu is here. Then after that, you count how many displacement in X, 1, 2, in Y, 1. Okay? That's the way motion tracking is done by human eyes, right? So the keyword is finding the same pattern. Okay, image registration. Good? Right. Good. Okay. So, the big question is how can we program the computer to identify this and this is same? And if I ask this, student will say, well, A is equal to B. Yes, mathematically speaking, this means A and B is same. But if I write down this in program, what will happen? If you write the program, say A is equal to B. Does anybody know?
A will become B by
Right? You plug the B into A, right? Replace A with B, right? Right? So that's not exactly the way we would like to check is A same as B. Good? Then what should we do? What kind of equation should we write it down to check A and B, are they same or not same?
one more
Equal sign. If A and B is same, what will happen? A plus B is what? A minus B is what? A minus B is there, right? Right? So that's the way we can make computer learn. Okay? I have two images, A and B. Are they same? Computer will say, okay, I'll take the differences. It's zero, the same. Okay? But usually it's not so straightforward. Usually this will never get zero. Usually we can get very close to zero, but it's not. Okay? So, but basic idea is to find out is image A same as image B, basically A minus B. If it's equal to zero or almost zero, we can say computer will tell us it's the same pattern. Good? Usually we will set the norm, okay, cost function, make it square, then minimize it. Good? Okay, and this process is called optimization. Okay. Right. Oh, this we did it. Okay. So here we go. Example. Right? This is my inner. This is a quite famous image everybody uses in the image processing board. Okay? Size is exactly same. Right? Size is exactly same, but everybody can tell they are not same pattern, right? Right? Then if you A minus B, you get quite messy image. Good? Okay? But if I do inu minus inu, it's exactly same image, so it should be zero. In the black and white image world, zero is black, right? Good? So this is a way you can quickly ask the computer to tell, is this image same as this image? Yes, no, yes, no, yes, no, yes, no. Then keep searching the space. Okay, that's the basic idea of region-based, okay, pattern-based tracking. Right. So box matching or block matching is basically using this relationship. This is the center of the image, okay, and that is only subjected to displacement, center displacement, and in x and y direction. Use this as a function to keep changing u and b and u and b and u and b, and try to find the pattern. Okay. Right. So, okay. Basically, block matching is basically change the u and b each time slightly. So, move to here. It was white, so you turn into a negative, 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 negative. Indeed, in the second frame, it was here. So do minus, then it will become zero. Then computer can quickly do this. Search, 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 take the difference, take the difference, take the difference. This is the only black image, zero. Then computer can say, after doing the block matching, computer will say, inu move to here in the second frame, hence displacement is 1, 2 in x, in y direction is 1. That's the way block matching does the tracking. It's very simple to program, okay? And today's computer can do it very quickly, okay? But one big problem is in this equation only assumes displacement in x and y, no assumption of rotation, right? Right? This equation, there is no sine, cosine, nothing. So if my inu in this image rotates, then this algorithm may encounter the problem. Good? That's the problem with the block matching. But still, very powerful method. Okay. Right. Okay, so our algorithm wise, this is what should happen between frame 1 and 2. Usually select the region, okay, target object, okay, box, then you should, and then after that, we will tell the computer to search this larger area. Okay? This location is exactly same in next frame. Then after that, this image is cut and starts sliding, plus minus, minus, 0. Okay, I found out this could move to here. Okay? Right. And then later, digital image coordination was invented. Okay? Because people noticed the image, when moved, it will not only translate, it will change the shape and rotate. That's the most challenging case, right? Let's say here's potato that we captured in the frame 1. Later that potato rotated and elongated. Good? Okay, that happens a lot, okay? So this is a very fair assumption, and solving this kind of problem, usually we use a technique called continuum mechanics, okay? This was invented by a mechanics person from University of South Carolina in 1980s. Okay, so they introduced the assumption of the object rotated, deformed, okay, so on and so forth. Then instead of just including the displacement, okay, rotation part, they included rotation information as a share. So this function, they set up a little bit more complex function here, saying from here to here, displacement in x and y, we don't know. U and du dx is the strength, okay, stretching x direction. dv dy is a stretching y direction. This is a normal stretch, right? Okay. Then share and plus rotation is included in here. Good. So 6 unknowns for this case. Okay. So optimization part is more complex, but that was the clever invention of this group. Okay. 1980s. Right? It's impressive, isn't it? Did we have digital camera in 1980s? I don't know. Yeah. Anyway, so use this mathematical function, then assumption, they started it. So basic algorithm is basically, this is my first in, right? Then assume you pick the 6 unknowns, okay, from the starting number, you try one, then Inu's image will move to here. Okay? Right? Okay, this is the first try. Obviously nothing. So if I do this minus this, it will not become 0. Okay? Then we know, that's the wrong assumption. Then you change the value again to beta 2. Then you will move to here. Then this minus this. Actually, this minus this, sorry. Then it's not same, so it's not 0. Then repeating the same thing again, using the optimization, and again, computer loves to do that kind of things. Then you finally pick the right function here, then transform to here, then this v dash minus the image of the Inu in the second frame, take differences, it's 0, bingo. Then you found out 1, 2, 3, 4, 5, 6 information. Good? Alright, then beauty of this technique is you can kind of find out the displacement of this center. Okay? Also how much stretch happened. Okay? Also we can find out how much shear and rotation, all the information included here, happened. Okay? That is the advantage of this DIC. Alright. Are we okay? Good? You just need to know the big picture. Good. Okay, then using the tracking algorithm, you can track this object. I use this video to teach the dynamics class. Everybody took the dynamics, right? Okay, then you learn the impact program. Remember impact program? Yeah,
then this is obviously, this person was kicking this ball, so that's an impact problem. And that's why this was one of the projects. Okay, so as an example, if you know the DIC, you can apply many places. In my case, I apply to analyze the video image captured from gradually stretching peak tendon. Good? To find out the strain and stress. Okay? Right, so here's the example. Okay? You can view this as a rubber or human tendon. Okay? And we capture the video of non-stretching all the way to 10% stretch. Good? Okay? Frame 1, frame 2, frame 3, frame 4, blah, 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 all the way to here. 10% stretch. Usually frame rate is 16 frames per second for the ultrasound. Usually we capture 5-6 seconds, so 70 frames in between here. Good? Alright, so I capture the video, okay? So since this is the video, I can put the digitized marker here, right? Good? Okay? Then let's say at the end of the video, that tendon stretched exactly 10%. Good? Good? Okay? Using the testing machine, you can achieve this easily. Then what will happen to this marker A, B, C, D? They will simply stretch, the spacing will stretch. 1 centimeter will become 1.1. BC is 1 centimeter, it will stretch to 1.1. Here, original spacing was 1, so here it will stretch to 1.1, right? Good? Okay, so this example is saying if you have an intact, non-damaged tendon or rubber, if you do this video capturing, put the marker, track it, calculate the spacing, after the stretch, spacing is exactly the same. Good? Good? Okay. Alright, then what will happen? Right? Let's say we have a tendon, shoulder tendon. This is quite a big problem for the shoulder, especially the male shoulder. Okay? Most of us have a tear, small tear. Okay? So let's say we cut this part, good, of the tendon, and we do the same thing, stretching from non-stretch all the way to stretch. Then what will happen is this cut part will open up, right? Are we okay? Okay? Alright. This is not rocket science, right? Everybody can guess, right? This cut after stretching, it will open up, okay? Alright, if I ask the patient to do this, usually that patient is usually already painful here, so never gets here. But that's the idea. Then what will happen between the marker space? Because this part is bottleneck, so this part between B and C gets stretched a lot, okay? And surprising thing is spacing between A and B, C and D doesn't change much. So from here to here, 1 centimeter stays 1 centimeter. Here 1 centimeter stays as 1 centimeter. But as a total stretch, 0.3 centimeter. So most of them happens here. Make sense? Good. So this example is saying if you have a tendon, cut tendon, capture the video from here all the way to here. If we analyze the spacing change, at the end what we will see is from here to here, no stretch. From here to here, no stretch means no strain. But from here to here, very high strain. Good? Alright. It's quite boring, I know, but when you're doing research, it's not that easy. Okay, so this was the my testing. Okay, pig tendon, not the human tendon, so you don't worry about it. Okay, and here you go. Video stretching, right? Okay. this is the last frame. You can see the cut, small cut open up to inverted V, inverted V2 cuts. Okay. All right. Then I put the digitized marker, roughly 200 here. Okay. Starts tracking by DIC. Again, as I said, good part of DIC is it can track the displacement and strain, right? Right. At the end, I would like to see the strain distribution. Okay. Right. Then this is the second image. Okay. It jumps around. Then, with the help of smoothing this and that, okay, at the end you can show the strain in horizontal direction. Good. Okay. This was the cut. This part is close to this part. This red zone is the overstretch correspond to this cut. This part we don't have the cut, but how come there is red? Because the tendon, when they stretch, tendon is not straight. When the tendon is in the body, usually it's twisted. So when you stretch it, it will do this. So that's why sometime at the end you will observe the high strain. Good. So this is the example of if you know how to apply the computer vision based motion tracking, this kind of thing can be done. All right. Okay. Then I think I have to show you the software, right? Okay. So again, the homework is this. I'll add a little bit more. Well, maybe it's okay. This video is 30 frames per second. Okay, and this segment, this is my finger. Okay, we would need this information for calibration. This space is 2.5 centimeter or 0.025 meter. Good. Right. Hey, but instead of that, we will do other videos. Okay. So. Does everybody have this? Wait a minute. Oops, daisies. I didn't save it. Where is my zip folder? Here we go. Okay. Grab the zip folder. Okay. This is the code I created for the class and zipped in here. Okay. Comes out to the desktop. Good. And also you can find the user manual. User manual was somewhere. Where was it? User manual is not with me, but I posted in the, I asked Bella to post in the Google Drive. Here we go. Okay, you can take a look at this user manual. Okay, this is the user manual of how to use it. So basically I will go through this. Good? Okay, so is everybody here? Everybody? Did you grab the zip folder? Are we here? Okay, then you have to unzip it. Okay, here we go. Oh my God, I don't know how to go from here. Everything is Chinese. 凯南 unzip 是哪一个？最上面吗？ 这个 OK, right. So if you are seeing something like what I'm seeing, the label is Chinese. Okay, you have to come here, right click, okay, and here you go, 7-zip. And come to here. Good. We would like to unzip it. Okay. Then it will create the folder, and here you will see all the code I created, plus some junks. Are we okay? Are we here? Do you need more time? 再说一遍。sorry. Okay. Okay, then I can do it here too. So what I did was here, right? Move the cursor here, right click, right? Then there is 7-zip, and 7-zip and come down here. Okay? Right. So right click, this menu comes up. 1, 2, 3, 4, 7-zip. It will come up. Then 1, 2, 3, 4, 5. Then it is, I think, 解压缩字, right? Unzip this to this folder. Good? Sorry. So everybody was on logged in. Oh, sorry. Then please log in. CAE PC room, but when you log in, on the left corner it says 中文 and English, so you should select the English. Are we okay? When you move the mouse to the left lower corner, okay, it says 中文 and English. Then you should click the English, then key in CAE, no space, PC room. Then your situation will be better. Use everything in English. Are we okay? Oh, okay.
You need to go to the website. I have all of the link to our group. Or you can just directly take the Google Chrome and type in the USB which is show on the screen.
Okay. Sorry.
Everyone can go to this website. You can type in this link, and then the attached files are over here. Just download all.
This part is how to use the software, so we can go through this again in the afternoon. Back there, yeah. But everybody who can download the MATLAB needs to download the MATLAB. Okay? I know the Tokyo Tech student may have a difficulty download and activate it because different IP address. Yeah. Any questions? Everybody? Any questions? Okay. So what you should be able to download is this video, okay, and also so this zip folder and this video called Soccer Kick, okay. All right, those two things we need to download to play with it now. Are we here? Yes. Are we done with the downloads code and this video? ダウンロードしました ?ZIP のファイル。Okay, and after you are done with the downloading zip file, okay, you have to expand that, right? So that means right click, right? My instruction is Chinese, but you see exactly pretty much same thing, right? Just English. Okay. To unzip the file, you right click, okay, and come down to the zip, 7-zip, okay. 7-zip, then this one here, video folder NTUSD June 2024. Okay, then you select that one, then at the end, you select this one, good. Then this will create another folder, unzipped folder looks like this. Are we here? Are we okay? Do you have this folder? Do you have this folder? Okay. All right. Then we are ready to start MATLAB, right? Okay. The MATLAB you can, if you have MATLAB icon here, you double click. Okay. Or you can find it from the menu, right? You scroll down, you can find out the MATLAB somewhere here. Here you go. Right? This is okay, but usually MATLAB is on the desktop. Good. Double click. Okay. Hey, who needs more time? Who needs more time? Okay, all right. Are we okay? Are we here? Okay, you have this folder, right? You have this folder and the video. Maybe we should create a video folder, right? Hold on. I will create the video folder. New folder. Okay, temp. Okay, then I will move my video to here. No, actually, I have a video here, so I'm not going to do that. Here. All right, so MATLAB. Have you started the MATLAB? Have you initiated the MATLAB? Are you here? Everybody? Who needs more time to get here? Sure.
What is you have a license?
Are we here? Good? Everybody okay? All right, so MATLAB, the center part is the workspace, right? If you 1 + 1 hit return, give you it, you can use it as a calculator. Okay? But first things what we have to do is, since all the code is in this folder, so we have to create the path. Tell the MATLAB, let's go to that folder. All the code is there. To do so, you come here. Okay. You select this browse for the folder. Good. You browse for the folder, click it. Right, and desktop. Yeah, this is a folder, right? Good. Are we? You select this BL folder NTUSD June 2024 and open. Good. Then if you reach successfully, the pathway shows up, right?
then all the code plus some junks appears. Are we here? After you start the MATLAB, okay, this part is white, blank, and this was blank, okay, because MATLAB didn't know where to go, which folder to grab and to look into. So we have to tell the MATLAB, please look at this folder. To do so, you have to come here. That's called browse folder. Okay, here. Good? All right, then my folder is on the desktop. Where's my desktop? Here we go. Right? Then all the folders on the desktop shows up. Then my code is in this folder, so you select this. Right? You select that one, say yes, then we will get here. Are we okay? Are we here? How many of you have used MATLAB before? 1, 2, 3, 4, 5. It is quite convenient. So, yeah, it is quite convenient, and many laboratories use MATLAB or Python. And hardcore researcher will use the C++ or something. Yeah. I'm not hardcore, so I'm not going to use it. Yeah. And today, computer is fast enough, so you don't need to compile it. Easy to program is way more important. Yeah. Are we here? 皆さん大丈夫ですか？問題のある方は有没有人有问题？可以了 OK. Alright, so we see we are in the folder, then we can run the program, okay? Then that program is called virtual lab, okay? Virtual lab is capital. So in here, you have key, okay? Virtual capital lab. Okay, good? Okay? Right, so that's what we're going to do. Good? Right? I type it. Okay? No, not the. Good? Okay? Okay, good? Alright? This is the workspace. When you use MATLAB, everything you type here, basically. Okay, the name of the program package is called Virtual Lab. Okay? Good? But you have to be careful. This is capital, capital. Good, then you hit the return, then window program shows up. Good? Alright? Okay? Alright, then after this, we will just use the windows. Okay, so, but we cannot get out. Do not click the cross. We minimize it. Okay? If you click the cross, it will close everything, so we don't. But we don't need to look at this space, so let's minimize it. I just need to see it. Good? Okay. If I compiled it, then we don't need to worry about these things. But are we okay? Here?
Okay, so that it has two modules. One is the video edit modules. Okay, this function is basically you import the video, take a look at the video, and some video is too long. Okay, we just need a certain segment of the video, then you key in, I need a video frame 400 to 500, then you will cut it and save it. That's the idea, right? Okay, here is the example, right? So original video is something like this, right? Original video is this. As you can see, nobody is here. Finally, this person came in around 6 seconds, okay? If you want to start tracking, maybe this is okay. He is in, ball is in, okay? They kicked it, ball is gone. So that means that frame is wasted too, right? If you want to analyze the impact program, we just need this segment, okay? So video edit module is created so that we can just cut out the important video frames. Good? Everyone okay? So let's go to the video edit. Here we go. Are we here? Everybody? Are we here? Do we need more time? Okay? Alright, then we are running out of time. I'll just go through. You guys just stay put, okay? So import the video. Here you go, okay. Then I have to find out the video location. Okay, my video is here. I click the circle, click here. It takes a little bit times. It's in. You can play. Okay, but I can just say I know the frame I want is 480 to 520. I know it, so I key in here 480. Okay, 520. All right, then play. Oops, daisy. That's too long. Let's make it 100. Oh, maybe let's change it a little bit shorter. Oh no, that's okay. That's okay. How about 30? That's too much. Right. Still 480 is better. Good. All right. Then now I know this is okay. This person is here. Ball is not gone. So I think analyze this part. Right. Then I have to save it. Okay. Save to ABI. We select this. Okay. Usually I name this as a frame. Okay. 480 to 500 was it? Yeah, 500, right? Okay. Then it is going to analyze, to cut out the video segment. Good. All right. Now I have the perfect video segment. I can analyze. Okay. Then we can go to the dynamics module. Okay. Then import the video we just cut out. I will repeat this afternoon. Okay. You just need to watch what I do and get the rough picture. All right. So this is the video we can analyze. Good. And it will ask us what is the frame rate. Okay. This video, specific video is 480 frame rate. Good. So 480 frame rate. Good. And next one is the calibration. Okay, measure the key dimension. Okay, there is no measurement here, but what we know is the soccer ball number 5 diameter is what? 0.3 or something? Okay, so we will measure, okay, pixel measurement of diameter from here to here, once, twice, 3, 4. Then here we will key in 0.03 or something. Good. So that we can convert pixel information to meter. So measure object. So from here, draw one line, go one more line, go another line, go. I just measure the diameter of the ball in pixel, okay? And the diameter of the circle, let's say, I don't remember, 0.4 something. Good.
0.4. Good. All right. Then I would tell the computer I would like to define the tracking point. Okay, here. All right. So I would like to track this knee, one, shoes, and the ball. The last object you have to double click. Done. Good. Then it should track. Oops, stuck. So I have to change the dimension. Sometimes it will stuck. Okay, change to the bigger window. Okay. Okay, and track it. Good, done. 3 points are tracked. Then I would like to track the vector. Let's say I would like to track this vector from here to here, here to here. 2 lines. So I say I would like to track vector. How many vectors? 2. Okay. Then I have to define from, either way is fine. We can from here to here, but I would say from here to here. That's 1 vector. From here to here, another vector. Done. Then calculate the length change, rotation change of the vector. Done. Then finally you want to see the result of both. That's it. Got it? Then you want to save the video. Okay, save the video first. Okay, track this as usually I say this is the track. Okay, oops, sorry. Fine. Video is saved. Then I would like to dump all the data to Excel. Then you click here. And this one doesn't tell you anything. So it feels like doing nothing. But everything is saved, right? Everything goes well, then you can see the Excel file here. Good? All right, so that's the walkthrough of the